Hello everyone, today we are going to have a video presentation for our subject Analog Electronic assignment, and this video is presented to the Dr. Ahmad Sahiquin, which is our lecturer for Analog Electronic, and our group member consists of two, which is me, Hua Seng, and the Hua Kai. So let us begin. First of all, our objective of our assignment is first to design the amplifier circuit using the knowledge that we learned through this subject, and second to study and measure the frequency response of an amplifier circuit. So for this assignment we need to get a result from theoretical, practical, and a simulation. So we are given the task to design a circuit about the BJT CE unbypassed bias. So this is the given configuration from the task. Okay, first of all, what is BJT or bipolar junction? BJT is used for two functions mainly. First is switching and to amplify the signal, and it manufactured in two types, which is NPN and the PNP. So they are the three lead of the bipolar transistor that are emitter, base, and collector. And the BJT work as the current regulator, which is allowed the small current to control a largest current, bypass it. Okay, so the second is the common emitter configuration. So as we can see from the figure, base and the common emitter is as the input terminal, and the collector terminal is at the output terminal. So simply say the common emitter is a inverting amplifier circuit, and the output signal have the 180 phase shift to the input signal that we get. So here is the figure. As we can see, the input and the output there is totally inverse 180 degree. Okay, first of all, this part is about I'm going to explain about the theoretical explanation. We need to design the CE unbypassed IE through the two analysis with DC and the AC. From the DC, we need to get the IB current for the base and the IC current for the collector. And second, the AC, we need to get the AB, which means again for the formula for the AB is V out over V in. Okay, first of all, the DC analysis. C1 and C2 is the coupling capacitor, and we need to assume all the capacitor inside the circuit are open circuit, and then separate the VCC, which means VCC need to connect to the RB and the RC, and then we should divide it to the front side and the back side. So here is the front side and the back side. So after we connect the VCC and connect to the front side and the back side, as you can see, we use the mesh analysis to analyze the circuit. Okay, as you can see, VCC minus IBRB, negative VBE, and negative IEIE. So after we analyze, we will get the IB equal to this formula, and backside also we use the mesh analysis, then we will get IC equal to this formula. Okay, from the AC analysis, first of all, we need to have a VCC grounded, and all the capacitor are the short circuit. And here is the small signal analysis for the BJT. It is almost is from the previous circuit, then we analyze to the small signal like this. So here is the voltage in and the voltage out, and our IE is here. So base, emitter, collector. So from here we will get our AV equal to V out over V in. After we simplify, we'll get this one, our AV and the IE equal to 26 milliwatt over IE. Okay, now we come to the CE amplifier frequency response. In here we will see the frequency response of the CE. Bandwidth mean Fs minus Fl, which means the higher frequency minus the lower frequency. So inside this range is the bandwidth. So as you can see, at the negative 3 dB, it will cut off, and later it come to negative dB, it also will cut off again from the frequency response. So our gain, we get our AB from using the formula 20 log V out over V in. So the frequency response will allow us to see how the output gain and the phase change at the particular frequency. So the graphical representation of the frequency response we draw on the called the board. Okay. So here's the figure with the C amplifier with the capacitor and the parasitic capacitance. So each word okay. First of all, CS, CC, and the CE. These three capacitors will determine the low frequency, and meanwhile the CWI and CWO is the wiring capacitor, and CWO, CBE, CBC, and CCE. These three frequency capacitors will determine the high frequency. So to find the low frequency, we need to find the FLS and the FLC using this formula. And to find the high frequency, we need to find the FSI and the FSO. So my group member will continue with the other part. That's all for me.
Good evening to Dr. Sharikin. For now, I will proceed for the results. So this is the simulation results from our assignment. Our assignment is BJT, unbypassed bias, common emitter. And we are using multisim to simulate the result. So this is the circuit we draw. And then now I'll show you the oscilloscope waveform, the output, and the input. So this is the gain, voltage gain that we got theoretically, yeah, and which is similar with the simulation voltage gain. And so this is the frequency response of the BJT amplifiers. As you can see, it is much complicated than the one before, where we have additional capacitors. And this is the board plot that will be shown later. This is the oscilloscope. This is the AC. This is the DC. And so this is the simulation results for the frequency response. As you can see, this is the output of the oscilloscope of this frequency response. Next will be the board plot. So yeah, this is the board plot from the simulated result for the frequency response. Next, we proceeded to practical in order to compare the practical to compare the difference between practical and the simulated results. So this is the circuit we constructed by using a breadboard and the components we requested from the component store. And then now I'll show you this an example from the frequency response. This is the an example of 20 Hertz, where you can see that this is the second one is the input, which is the 20 Hertz, and this is the output, where you can see from the peak to peak of the output will be 5 volt for this 20 Hertz, and then for the peak to peak voltage of the input will be 2.09 volt. Next will be the 100 Hertz, where I choose to show you for the difference of the voltage peak to peak, where this one will be dropped for a reason from 5 to 3.9. I believe that this is the frequency that is making the voltage drop. And then to show you that the next one will be 100 kilohertz, where it has a very high frequency, and as you can see here. And then our peak to peak for the output will be 9.8, where it is increased drastically. So the input will be 1.45. So this will be the table that we got for the practical results, from 10 Hertz to 4 megahertz. So 10, 20, 50, 100, 200, 500, 1 kilo, 2 kilo, 10, 20, 50 kilo, 100 kilo, 200 kilo, 500 kilo, and 1 mega, 2 mega, 4 mega. So as you can see here, the voltage gain was 7.75 for the 10 Hertz, and it dropped a bit, at 100 Hertz, as I mentioned, that I believe that this is the frequency that is making the circuit loses the efficiency, I guess. And so after that, it will be 200. It increases, and then it increases drastically when we reach 500 Hertz, from 6.63 until 13.776, and therefore it increases as it goes until 16.60, which is 2 kilohertz, and then it remained there until 4 megahertz. As you can see, this is the practical result for our board plot. It started here, and then it dropped for the 100 kilohertz, and then it increases drastically, and it maintained at 200 kilohertz, 2 kilohertz, yes, 2 kilohertz until the end, 4 megahertz. So in conclusion, we are given this assignment to which is BJT, common emitter unbiased, with the configuration as stated. So after we do this assignment, we now have understand more about how the BJT works as amplifiers, and also we are able to analyze the frequency responses as well as the gain of the circuit. Thank you very much.